This paper should have been given by Sun Jun. He had a little bit of a visa issue, so I'm going to deliver it, and hopefully I can do a decent job on his stuff. So for a number of years now, we have been looking at what could be a real clinical application of photoacoustics, where both a system matches into the way in which clinical practice actually works, and also there's added value from the photoacoustics. And so what we've looked at is ultrasound-guided drug delivery as one potential for this. First of all, ultrasound, as we heard in the plenary session this morning, has been used for needle guidance for a long time and is pretty robust tool, even though it has some limitations in terms of its orientation dependence, and that there can be contrast issues, especially when you're using small gauge needles in doing that. But the big issue has to do with the actual delivery of the drug itself. Current systems can use bubbles to guide, but these are very short lifetime and relatively large size, so it really can't show you where drugs are diffusing, and they certainly can't tell you about the drug in the long term and its uptake and utilization. The one good news that we have had with photoacoustics over about the last 15 years or so has been the development of a wide range of molecular agents with tremendous sensitivities and specificities using a lot of physical effects, which should be allow you to monitor drugs and the utilization and uptake of drugs. I will talk about one such agent used here, but it's just as an example of the many possible agents that can be used in a drug delivery scenario. Okay, so on the system side is, and this is old and we've shown this many times, which is that most photoacoustic systems are like the Wizard of Oz, which is do not look behind the curtain, ignore that man, because behind the curtain is usually a system like this, which is this large laser system. We have gone to a compact. You're going to hear later in this session an invited talk about alternate methods for a compact lasers, but this is clearly the way to go in order to bring something to delivery in the clinic. If you looked at laser that we're using now, you can fit in the palm of your hand. It's a high rep rate, what we call medium energy, meaning single digits of millijoules. Up to now, we've got up to 6 millijoules in a device. What I'll show you today is a 2.5 millijoule device. And at last year's conference, we presented how the system works, and in the recent transactions paper. Building on that, we've gotten a little funding to actually develop a real system based on this principle, which is an integrated ultrasound scanner and photoacoustic delivery system, in which we use the switching methodology. So it's not parallel illumination, but actually a switching, which is done at a very high repetition rate. And we have designed an optical switch to work with the high repetition rate laser to do that, and it's currently under construction. So what I'll show you today is an emulation of that specific system that we've done in the lab. And the key point is, for us in doing this study from the system side, is that we always worry about the peak fluences that we have per pulse, but when you do rapid scanning, you also have to worry very much about the radiance limits, which is 1 watts per centimeter squared, and doing that while maintaining an SNR which allows real-time imaging. So here's the system. So this is the system that we're building. Is here it's a high-frequency ultrasound transducer, or 10 megahertz transducer. We're going to have 20 fibers which are delivering this, and the pulse repetition rates on the order of 1 kilohertz up to about 1.5 kilohertz. And the design is to stay within the safety limits of functioning at 1053 nanometers. So we have the fluence, the per pulse energy per unit area, but also the radiance is to stay within that limit as well. So we've done a bunch of, Sun Jun has done a bunch of simulations in designing the fiber sizes, the fiber distribution, the scan formats, and all that, to give us a sweet spot of imaging down to about 1.5 centimeters to 2. So depending on concentrations of agents, we're looking at working down to about 2 centimeters in this design. So this is primarily for peripheral applications. So, okay, what I'm going to show you are the results that are then not with the integrated system yet, but with an emulation of that, which is done with a multi-galvo scanning system, which can deliver the pattern, precisely what we expect to get from the fiber optic delivery system, and scanning through this. And doing it here, optimized at just under 1 kilohertz for the rate. The pulse energy is 2.2, I said 2.5, sorry, 2.2 millijoules is that. And the frame rate you'll see is an integrated full frame at a 36 hertz rate, which has ultrasound and the photoacoustics, and we stay within the 1 watt per centimeter squared radiance limit. So here's the type of images you get from this. So again, this is a single shot. So you're scanning the photoacoustic beam through here and reconstructing images from that as it scans, but then pasting it all together at the 36 hertz frame rate, which has both the integrated ultrasound signal as well as a full frame of photoacoustic signal in it. Okay, and so this is just showing a needle that's already been placed with inside some tissue, and it's a 22 gauge needle, which is typically used for peripheral drug delivery. Okay, so what would a procedure look like? So first of all, and I'll just let this play because for about a minute, and then I'm going to conclude. Is what you're showing is an emulation of the typical types of procedure that you would use for slow release delivery of a drug over hours to days, using a preparation which is brought into a polyvinyl. Well, we use polyvinyl alcohol. You wouldn't use polyvinyl alcohol in a real tissue sample. You would use a hydrogel, but this was easy for us to do. But the contrast agent is Polypyrrole, which we've used in other nanosystems. And why we picked this one is it has a very strong optical absorption at 1053. So we can tag it, and it's a molecular agent, and it's an approved FDA material as well, used for neural implants. So what you're looking now is here is on the left side is just the ultrasound component of this. And I'll wait till it starts the cycle again, and I'll describe it. So as you start a cycle, you're going to bring in the needle, so you can see in the ultrasound, but you can also, of course, see the needle itself in the photoacoustics because it's a good signal. But unlike the ultrasound, now when you eject the molecular agent, you don't see anything in the ultrasound because there's nothing at the micro scale, it's only at the nanoscale. Whereas, of course, in the photoacoustic, because we've picked the agent properly, is we can see that, we now remove that, and that is the drug source. And now you can just monitor that forever, not forever, but as long as that is there, and in case in this slow release case, you can monitor it over seconds, minutes, hours, days. We've done one experiment where we looked 1 day later and can see just the simple diffusion of that molecular agent in the region. So unlike, this is an added feature that ultrasound really cannot provide in this type of environment. Okay, so I think you get the idea. So let me just conclude on that. So what we have done is showed this real-time imaging. Interleave, we call it PAUS, just for local reasons, but it's a photoacoustic ultrasound, real-time. At frame rates here showing at 36, we've gone up into about 60 hertz with this same setup. The scan geometries here have been optimized for 10 megahertz ultrasound operation to a depth of about 2 centimeters for peripheral applications, and we're looking at a potential clinical application, which is the needle guidance, which again the ultrasound can do pretty well by itself, but it's the drug delivery monitoring using molecular agents targeted to this application and over depths ranging from about 1 to 2 centimeters, so primarily peripheral. Of course, I should have stated this at the beginning, this also can be used for discovery applications in small animals. We can do pretty much whole animals with these types of depths, and again, looking at the way drugs are delivered and drugs are utilized in real time. So acknowledge the funding sources and colleagues at the University of Washington. Thank you.